Yes, okay, thank you. Hi Oslo, hello world, welcome to the .NET 7 API diff. I am super excited to be here, being back in Norway, being back in Oslo at the NDC. And in this talk in the next 60 minutes, I would like to show you what new APIs, that is all the new types and all the new members that we get when we upgrade our target framework from .NET 6 to .NET 7. Now there is a lot of new APIs in the BCL, the base class library that comes in box with .NET. We won't be able to go through all of them. I hope that I've selected a slice that fits for all of you. I'm using the word slice with intent because there will be spans. And I am not going through other libraries and programming models such as ESP.NET Core or Entity Framework. They all have also a full year of new changes, but since we only have so much time, I will be focusing entirely on the BCL that you can use anywhere that targets .NET 7. My name is Stefan Po. I'm from Austria. I am a JetBrains community contributor, a Microsoft MVP, and the co-organizer of the .NET meetup in Vienna. I'm also semi-regularly streaming on Twitch and YouTube, and I'm putting my socials there. I can give at the end I have a slide for that if you have any follow-up questions that I'm not able to answer today. All right, .NET 7. Where do we start? I need to go cheating. Yes. Who has visited Philip's talk about the new C# 8, 9, and or is it 9, 10, and the 11 features? Wow, a lot of hands. I see a lot of C# and .NET developers here. And I think he covered briefly static abstract members. And there is this thing called generic math. It has been previewed in .NET 6 with C# 10. You were able to turn it on with a preview flag. That is, if you happen to, say, enable preview features. But now it's fully released and supported with C# 11 and .NET 7. What generic math is a term. It's not really a feature per se. It's a combination of features that then the BCL uses to produce generic math. So with C# 11, we can have static virtual members on interfaces and static abstract members on interfaces. We can also define our own checked operators. Previously, per default, everything is unchecked unless you make your operations in a checked scope or set on your project level. Where is it? Overflow, underflow. There it is. Check for overflow, underflow. Then per default, in the entire project, unless you have an unchecked scope, every operation is checked. That is, if it overflows, it will throw an arithmetic overflow exception. And now we can, with checked operators, we can define both unchecked and checked operators depending on the context. The unsigned shift operator is new, and also shift operators in general have been relaxed. So what does this all mean? We can write an interface. Is the font size good enough for the people in the back as well? Thumbs up, thank you very much. So I can define my own interface, call it the my number interface, and then I constrain the generic type basically to itself. This is called the curiously recursive pattern. And now I can define some static members on it. So I have some static abstract members. I define 0, 1, and -1. can also have static operators. So I define the plus operator. By default, that's the unchecked operator as abstract. And I also define the checked operator. Here's the new keyword, or old keyword, but now repurposed, but a virtual member. So now if I have a type, in that case a struct, which implements this interface, we need to implement all of the abstracts. So if I were to remove, to comment out the implementation of the -1, now we would get a compiler error that says -1 is not implemented. But with virtuals, since we supply a default implementation here, it's optional to implement them. We also implement both the left and the right shift operator. These rules have been relaxed previously. The shift amount had always had to be of type integer, or anything that is implicitly convertible to an integer. Now you can have any type. And also declaring the unsigned, this the new white shift, unsigned white shift operator. And so what we can, the big benefit now with having those static members on this interface is that I can, this is where the name generic math is coming from, I can write algorithms that are not depending on a specific type, such as int or double, but on this interface. And then any type which implements this interface could run this algorithm. So I'm having here a sum algorithm. The thing is, what doesn't work now anymore, so the input is a read-only span. And again, we see this pattern that the generic type is basically constrained to this I number. And where do I start? I want to sum up all the numbers in this span, but I need to start at 0. But 0 is an integer. But we don't know if whoever implements this interface is actually having an implicit conversion from interface. So this is why we declared the 0 here. Or in the interface, we know any type that implements this supplies a 0. So this is how we can start. So on this interface, this is basically this interface type that we have constrained to. We say, hey, I want to start with a 0, and then sum up all the values. We are being here in a, oops, sorry. We are being here in a checked context. That means that we actually invoke the checked operator, the checked operator, of course, here. If we were in an unchecked context, it was the unchecked operator. And now we can have our algorithm. I'm allocating 3 of my numbers on the stack and using now this generic algorithm to sum them up. Since we're in a check context, my number, it's backed by a signed byte that is from -128 to +127. So if I were to overflow this, we will get indeed the overflow exception that this arithmetic operation has overflown. Now, if we would change this algorithm to the unchecked here, it now doesn't throw on overflow, but it actually wraps around, and now the result is -128. And I'm also having a little example with the right shift operator. So I'm printing this number, having 120, shifting it to unsigned white several times, and we see the representation here. And this is all, now this would work with any type that implements this my interface that I've defined. So the big benefit is that we can have types that implement specific interfaces, and then we only need to write algorithms once. And the .NET team has already made big use of that. So let's have a look at one little example. I'm having here, I'm doing some timing and some GC allocation check metrics, and then the arguments that the user passes into this command line application, I parse them all to an integer, and then call my sum method on that. Not my sum method, but this is the LINQ sum method. So let's run this test. oops, I should have a white screen there. So we have, how did I call it? Come on. Call it sum. So we can now say sum, and let's add 223 and 7, which should be 2030. And indeed, it's 2030. And we do allocate some bytes because this is we're converting all the strings to an integer, and there is some intermediate allocations in there. And it takes like 3 milliseconds. Now I want to switch to a generic math algorithm. So let me briefly change this to using span instead. And now we call into this generic version of it, which is way more code than the LINQ implementation that we had, but it's highly optimized. So what we're doing here is we allocate a contiguous set of memory on the stack if the input size, if the input length of the string we give in, of those string numbers, isn't too big, because with stack space you need to be very careful. Don't allocate too much on the stack, because otherwise we run in a stack overflow exception, and we can't recover from that. The application is gone. Now we want to parse those numbers to which version of the algorithm we want to use. Currently we're using int. And now what we see here is I'm now using a different interface. I'm using the iNumber interface. And this is actually coming from the BCL. And they have been added in .NET 6 as preview, now with .NET 7 as full. And there is basically the interface I showed you previously is a very small version of that. So we see we now have clamp on this iNumber defines a static virtual method clamp. So every number that implements this interface is clampable. And we will also copy sign. There is a lot, for example, max. So we see a lot of methods that we previously had on math, on system math and system mathf, now in this generic interface and these implementations. And for example, we also have a number base. In the number base, we see again 1 and a 0. There's also a radix. This is basically the base of the number. All binary numbers, such as int, long, float, and double, are binary numbers, so the radix is 2. Decimal in .NET is a decimal number, so the radix is 10. And there is a lot of interfaces which implement, or which force the implementer to implement operators, such as the subtraction operators. And this includes a unchecked and a checked version of the subtraction operator. And we have this for plus, division, modulo, all of the operators. So this is a lot of interfaces. And for example, the algorithm version that we are using here is we are using integer. So that's int32. And if you look at this implements now those interfaces. It implements I by binary integer, I min max, so we know how to get a min or a max from this value, and also a signed number. And all of the primitive types, long, float, decimal, also the big integer, in .NET, they now implement these interfaces. So I can write one algorithm one single time, and I can use it with every type every numeric type from the BCL, and also any user type from a library that I consume via NuGet, if they have implemented this iNumber or any of the interfaces. And so we now need to write an algorithm only one single time. That means we can heavily optimize this algorithm. So again, this is now a bit of an optimized sum version, where we also do some vectorization. This vector, I think this has been added in .NET Core 3. This is related to Hardware Intrinsics and SIMD. That is a single instruction, multiple data, where we can actually write with one instruction multiple data into this vector and then sum it up very fast. And we see now this sum is way more code, but it will end up way more efficiently. So if we briefly run that, if I have saved, what am I doing wrong? Yeah, there we go. I should save the program file. And now we see that we allocate significantly less bytes because we are now, those stringification is now happening on the stack, mostly, no longer on the heap. And we also don't use LINQ because LINQ usually involves a lot of allocations on the heap. And it's also significantly faster. This is for this very small input set of 2 numbers. I tested it with up to 10 numbers. When it's more like 1,000 numbers, then actually this algorithm falls off a cliff at some point, and the LINQ version is faster again. Because now the .NET team is also using this generic math and has significantly improved the performance of LINQ. So it's time. Well, not LINQ per se, but some specific implementations. So I'm having here a benchmark, having an enumerable. We actually fill it as what we will fill it is an array with size 4 and 1024. And we will be using min, max, sum, and average. So let's take a look at these benchmarks. The fast link. We see that on .NET 6, for example, min on .NET 6 took like 32 nanoseconds and allocated 32 bytes. That's the LINQ-related allocations of the enumerator and the iterator. But on .NET 7, we have 0 allocation, and it only takes 5 nanoseconds. And we see this for max, sum, and average as well. So how did the BCL team improve the performance so significantly? If we take a look at the implementation, we will see that there is a lot of generics going on. This is an indicator that they have implemented this with a generic math. And if you have a look at this sum implementation, now there's only one implementation of sum. Previously, there was many implementations for int, for byte, for float, for double, and so on. Now there is only one, which is generically reused. And the .NET team tries to get a span out of this enumerable. That is, if it's backed by, for example, an array. So if the enumerable is backed by an array, we can get this and just do a very quick sum algorithms. So we just iterate through the span and sum them up. This is very similar what we saw from the previous example. But if it's not an array, if it's a lazily enumerated, or a deferred enumerated enumerable, then we fall back to the classic LINQ style allocation, and this will now involve the heap allocation for the enumerator. And there is a lot of code now updated in .NET to use generic math to reduce a lot of code and then have those code paths optimized, because there's only one code path that they now need to maintain and can heavily optimize it. And this is the generic math feature and how it's used. Now we talked about LINQ. There is also more LINQ-related improvements. I'm again having a very similar benchmark here. But no, actually, let's get to the test first. Should be... No. There it is. So I'm having an enumerable here. And what we now have is an order method. Previously, we only had order by methods. So what we wrote previously is order by. And if I don't want to select a specific value, but the value itself should be ordered, then I would write something like this. Oops. X goes to X, which is a so-called identity function. So it's selecting itself and then giving it to the LINQ, to the enumerator implemented. But if I want to just sort by the element itself, there is now this new version of the method. It's just order. And there's also a version where you can pass an equality operator, equality comparer. And the same is also for order descending. And again, this gives a little bit of a performance boost. So taking a look at the benchmarks, comparing order to the classical order by, which does selection via the identity function, and the same with order by descending. And we will see a bit of a performance improvement. So if we order and order by, there is smaller improvement, and on larger sets, it's a little bit more noticeable, but on larger sets, we also have less allocation on the stack, so on the heap. So we will cause less pressure to the garbage collector. Now let's go to system text JSON. System text JSON now allows in the JSON reader, so that's a struct that is very heavily optimized. We have a new method, a new member where we can say if a value is escaped. So what I'm having here is a JSON string. Have you seen this way of writing a string, the raw string literal? Have you seen this already? No hands. So this is also a new C#11 feature where you can write the so-called raw string literal, which means now everything within this string is actually it's taken literally. So we have single quotes. They're actually interpreted as quotes. They're not terminating the string. And we can also format it nicely. So we see that the terminator here is on this line, which means that there is no indentation for that string. If I want to have that string indented, now it's indented by one level, because the terminator is basically this height here. So what we can't do is outdent it more than the terminator here, because we can't outdent it or indent it by -1. This doesn't work, so we get a compiler error now. And I really like this to write JSON-based tests, because now what the IDE is also doing, it's formatting. It's recognizing, okay, this is JSON, and it's formatting it nicely, so I can have nice inline JSON from a unit test. I'm having here an escaped string. And this new JSON feature now can detect, okay, is this value actually escaped? And there is a new method, copy string, which takes a span. So if the span is backed by an actual stack allocation, we can now allocation-free copy a string out of this reader. And the team is also using this, and this is how they make system text JSON so fast. And we can also now have polymorphic serialization with system text JSON. So I'm having here a base type, which is using the date only type. I'm also marking it as JSON required. Is also a new property which forces the serializer, if this doesn't exist, it will throw an exception. And I'm deriving two types from it, which is one is using time only, and one is just a string. Then we go create now a derived version of this type, so which has both the date and also the time. We serialize it, and then deserialize it back. So we do a round trip. Now I want to do an assertion on it. And this test is failing because it only contains the base version. The round trip didn't contain the serialization didn't contain the derived version, because system text JSON previously couldn't handle polymorphism. Now it can. So if we turn on, place those new attributes, the JSON-derived types, those are new attributes. And we are saying, okay, we can also declare a discriminator. So I'm saying that the base type has to discriminate the base, and the derived types, derived 1 and derived 2. So now we teach the serializer that this is a polymorphic type, and in the serialization, we actually get now at the top this $type discriminator. So the serializer emits, okay, this is now derived 1. So in the round trip now, the serializer knows, okay, I need to serialize the round 1 version of this, although I'm statically typing it to the base version, at runtime it's still the dynamic derived type, so we can also assert it that it is the round trip version of it. We can also set our own discriminator. Per default, it's type. So we can use another new attribute, the JSON polymorphic attribute, and with that we can pass our own discriminator name. So I'm calling this $discriminator. And now the test fails because this is no longer called $type, but $discriminator. It's failing because, oops, sorry. Oh, yes. Because we can also give a discriminator, can be either a string or a number. So I'm now giving this discriminator the number 1. So it's not just 1 here. Oops. And now this test will pass shortly. And it's green. So the discriminator on JSON should always be the first element, because this is how the serializer works behind the scenes. It looks at the first element, sees, is this a discriminator? Then checks the type hierarchy, can I match this? And then tries to serialize and deserialize it accordingly. And we can also define behavior if we don't know, if the serializer doesn't know which to serialize it to. This could be if I'm getting a type that's from a different assembly, and I may not have annotated this different type, so perhaps it doesn't work. And we can have different, 3 different strategies. We either fail, or we, for example, could fall back to the base type that is actually known. And this also works for the contract-based model. So you can also do this without the attributes, with regular C# code where you define your, I forgot the name of the type, but in the JSON type provider. But you can also do this declaratively if you don't own the type and can't place attributes on it. And more in the text world, Regex got a major overhaul. We now have 2 new big features in Regex, both a non-backtracking version of the engine, which in some cases doesn't fall in some recursive loop, and we also have a source generator. So we can, in the regular version of the Regex, I'm defining here, this is the new enum member Regex options, the non-backtracking engine. I'm also using the source generated version of it. So we have here this Regex, this generated Regex attribute. We can place this on any partial method. So we see this method is partial, but it still compiles. So it's not us that actually is implementing this partial method, but a source generator. So the source generator, via this attribute, sees, okay, we want to create a Regex for this. This is basically trying to find all the versions of my internet personas. And we are not using the backtracking, the non-backtracking version here, because that is not supported for Regex, for the generated Regex yet. And if we want to have a look at the implementation, we see that we are now in a generated file. And the .NET team actually added a lot of comments. So the source generator, which is generating this C# code, also adds a lot of comments. So you can actually see what the Regex is actually checking for. And the cool thing about source generators, we can also set breakpoints and debug the code that the source generator has produced. And source generation is very interesting in scenarios such as AOT, or where we are not allowed to emit dynamic code. For example, reflection.emit. This is not allowed on Apple devices. So on an iPhone, we can't do reflection emit because in code pages, it's only allowed to either write code or run code. But reflection emit would write code that is then at runtime, which is then executed. So this is permitted. It's a security feature. So we couldn't use on such systems which prevent code emission. We couldn't use this the compiled version of the regex, of the standard regex, because actually what's happening at runtime, the first time this regex is executed, IL code is emitted to the assembly once, which will take some time. So the startup performance of the first regex match isn't great. Every subsequent one, however, will then be faster. But we can't do this on restricted scenarios. Also with AOT, that's ahead of time compilation. This came in .NET 7 as well, and this further expanded in .NET 8, or will be expanded in .NET 8, where there is no JIT, no just-in-time compiler anymore. So the code is compiled at compile time for this target machine, for example, Windows 64, and then once on Windows 64 machines without the JIT compiler, which means the startup performance is superb because no code needs to be compiled at runtime to the machine bytecode. And now the source-generated version actually would work in AOT scenarios because there is no code emitted at compile time. This is all at runtime. This is all at compile time. And this is why Microsoft is pushing in .NET 6 and .NET 7. We now have like 5 or 6 source generators, and there will be more in the future. If you want to know more about source generators, I'm doing a talk on the last day of the conference. And now we have some tests here, basically doing some regex matching, and the result is both from the compiled version and also the source generated version is the same. And we also got new methods on regex. We have a count method. If in scenarios where we only want to know how many counts there are, but don't want to know more information about it. We just need the count. How many matches did we have? So this count is now the fastest version to do that. And we can also set a start at. So in this case, I want to start at the first semicolon. I am regexing those streams of mine, so we will now only find the second version, so the count is now 1. There's also a new enumerate matches method on it, which returns a new type, the value match enumerator, which is an enumerator. So that means it has a get enumerator method, and it has the move next method and the current property. So we can do, this is basically what a for each loop would do under the hood. Basically move to the next element, get our matches. We can get the index of the match, or the begin index of this match, and also the length of this match. Then we move to the next match. We actually found 2 matches, do the same again. And at the end, if we are at the end at this enumerator, it will return false. And this is the news in the text-based APIs. Now there's also big improvements in interop. I guess you can guess it, there now is also a source generator for interop. Having here an example where I'm invoking a Windows API to show a message box in both the classical way with the DLL import attribute, which is, again, under the hood, it's emitting IL code that is then JITted, just in time compiled, and then executed by the runtime, which again wouldn't work in restricted scenarios or in AOT scenarios. And so now there is a new attribute, the library import attribute, which is a generator. So again, it's a partial method that now the source generator is implementing. We can have a look at the implementation, set breakpoints, and it's now the source generator which does the marshalling as efficient as possible. So we can now use library import in AOT scenarios as well. Let's show a brief demo. So the, oops. So first the IL version, or the chit version of it, the MITS IL code, and which is then chitted. So it says, hi Oslo via the DLL attribute, and the same works for the source generator as well. If we run it with the other command, now it will say hi from the library input version. And AOT, I forgot to mention, AOT is very interesting in application deployment models which are short-lived, such as Azure Functions or AWS Lambda, where the application on demand is fired up, and then it may not be running for hours, maybe just runs for minutes. So every run in a classic deployment would invoke a lot of JIT compilation, and that would be a lot of time that we actually have to pay. Now with AOT, we can get rid of this JIT compile time and have faster startup, and also save a lot of money. And there is one last very interesting interop, also source generator, in .NET, which is the JavaScript interop generator. This only works within the browser, but I'm having here a Blazor application, but it isn't restricted to Blazor. It's just restricted to, we need a WASM runtime, for example, or we can run it in either WASM runtime, or we run it via the browser. It's not necessarily restricted to Blazor, which was previously the case with the .NET 6 and before JavaScript interop. Now with the new interop, I'm having here a couple of buttons and some texts, and let's take a look at the implementation and the callbacks. We call the methods, which now, again, we have a partial class and slap the JS import attribute on, which now does source-generated marshalling to the JavaScript behind. And we want to show a message box. We want to write to the console, to the browser's console. We want to read. We want to prompt some value. Now, if we take a look at the JavaScript, we basically call into this Windows alert, console info, and the prompt. And when we run this application, I do not. So basically, it's now running, loading the WASM.NET runtime into the browser. We can go to our page and now have these wonderfully designed buttons. We can, let's say, hi Oslo. And we had a show, we now interop into the JavaScript, which puts this alert box into our browser. We can also write to the console. So let's clear our console here and say, I don't know, hello world. And we get it printed to the console via the JavaScript. And we can also, for example, prompt, get this value, and now what the user enters here, some number 1, 2, 3, 4, 5, 6, 7, 8, 9, basically feed back to our page and print it to the console if we want to do that. And I'm having a callback button here. This is now the other direction. What we now had is JavaScript import. So we imported basically JavaScript, or we called into JavaScript. Now we can also do the opposite. We can have JavaScript call into our .NET, into our C# code. This is now working in the other direction via the JS export attribute. I have one more import, which calls into this callback method. And then in this export, I say from .NET with an incremented counter per invocation. Taking a look at the JavaScript behind the scenes, we have the callback that is invoked first. We basically get the .NET runtime, then import, or we get an export to our DLL, which is here. And then with this exports, we can call into our method, the get message method that we declared. So we say exports, then the namespace, fcu.pages, not the assembly name, but the namespace. Then we have here the name of our Blazor component. We call into the get message member, and then find an element in the DOM tree, which is called result, and print that to there. So if we now call into the callback, JavaScript is invoking our .NET code, and this works both ways. And again, it's source generated. So there is no marshalling done or compilation, JIT compilation done at runtime. All the overhead is done at compile time, so that the runtime is always fast. There is no performance impact at the first run. Now let's have a look what has changed in the bare system namespace. Previously, if we want via the app context, we could only get some ambient data. We couldn't set data before. Well, indirectly via the app domain. So now there is a new method, the app context set data, so that we can set data comfortably with the app context. We see a new exception, a new throw helper in the argument exception. So what was added in .NET 6 is argument null exception dot throw if null. This is a method added in .NET 6. This was originally related to the double bang operator. If you can recall this was a design proposal for C# 11, which means for any member, if we say string arg exclamation point, now the compiler would generate code that null checks this arg basically at the first line of the code here. But this feature then got stripped out, and what was left is the idea of those throw helpers. For example, throw if null. And what we now have is a new one on the argument exception, the throw if null or empty, which takes in a string and checks is the string null or empty and throws. And this pattern is particularly interesting because we actually hide the throw. So we have here the in check, we have here the if check, and this is a very small method. So this is quite likely that it gets inlined, which will then basically omit one method call. Every method call creates a new stack frame. It's very, very tiny, but in very hot loops, this could add up slightly. So this is interesting to have this version of throw pattern. And then there is this one method which actually does nothing else but the throwing. And we can now just call throw if null or empty, and we don't need to write this repetitive throw pattern all over the place. And this exists, so having here a test, if we pass in null, we get the null exception, we get actually argument null exception, and with the parameter name set to this argument, this is, although I don't pass it here, this is because also of a C# 10 and .NET 6 feature, the caller argument expression, which basically automatically at compile time sees what's the name of the argument that we call this method with, in this case argument. So if I were to rename this to my arg, in the equal check, doing here again name of, and it still passes because that's done by the compiler. If we pass in empty, we get the argument exception. So that's the string is empty, and if it's neither null or empty, it will not throw. There is another throw helper on the argument null exception. So previously we had the throw if null. This one we got in .NET 6. Now there is also a pointer version of it. I guess you need this rarely, but perhaps if you need it, you can make use of this very nice throw pattern here. and this works the same, but as with regular objects, with regular managed references, but now also with unmanaged pointers. We have a performance improvement in enum. Not per se, but if we want to consume enums. So if we want to, oh sorry, mixing up. So in enums, if we wanted to get a collection of the enum values as the underlying type, that means in our case, we have here the string split options, where the underlying type would be, the underlying type is actually an integer. By default, an enum is an integer, and we have 0, 1, and 2. And if we want to get a collection of this, previously it wasn't that easily possible. Now it is with this new method, get values as underlying types, which returns an array with these constants. If you have a look at the test, we can now check, okay, those are those 3 constants, and at those positions, they are 0, 1, 2, and they actually typed as integers, not as the enum type itself. And if we, this also now exists as an extension method on type. I'm having here my enum. I implemented this as a byte, and we see now in these tests, this is actually the byte that we get. So it's depending on the underlying type of this enum. We got some improvements in memory extensions, which again is very span related. Who of you has used span already? Span of t or read-only span of t? I see a couple of hands. A span is a, have I mentioned this before? A span is a representation, a view over a contiguous amount of arbitrary array. Arbitrary array, it could be backed by an actual array, which is on the heap. It could be also stack allocated, what I showed an example earlier, which is on the stack. It could also be some unmanaged memory, for example, provided by one of our interop scenarios that we showed earlier. And the span is now this view of this arbitrary memory, and it's very efficient because a span is a struct. And it's only a view of this memory. It points to the beginning of an element, or of this arbitrary memory, contiguous arbitrary memory, and the length. Again, could be array, could be stack allocated, could be native memory. And we can do a slicing on that, which means if we would slice, well, basically, if we have an array of 5 elements, let's draw a quick example. If we have an array of 5 elements, and I want to get the middle 3 elements out of that, I would need to allocate a new array with the size of 3 and then copy those values over. So we have heap allocations, which puts pressure on the garbage collector. Now with a span, still backed by an array, now with a span, if we convert it to a span, we could actually get a span view of this, which is now basically just pointing to this first element with a length of 3, 1, 2, and 3. So the actual array is not changing, it's still there, it's just the span is now pointing to a view, a smaller view of this. And this is called slicing. And what else we can do now with, once we have a span of contiguous memory, an array, for example, is implicitly castable to a span, we can do optimized operations on this. And in .NET 8, we got, for example, the common prefix length method, where in our case we have NDC London and NDC Oslo, and the common prefix length is 4, NDC and the space. And we can also use the same method with an equality comparer. In our case, we ignore the case, so it works for both if it now works case irrelevant. There's also new methods like index of any except. So if we have a span of chars, basically a string is in .NET backed by a char. So each character, that's a 16-bit char. So we can convert the string array to a read-only span of char, And of course, it's read-only because the strings are immutable. We can't have a mutable span of char over string because then we could mutate the original string, which would be quite unsafe. Or our applications wouldn't rely on that. Because there's also string interning, and if we would change this internal representations, hell would break loose. And we could now ask where the index of any except gets the first index of any characters except n or d or c, which in our case is the index 3, the space. There's also the invert. There's also a version. What's that? So yeah, so this is basically a params version of it. So we can pass multiple characters. There's also a span version of it where we pass in a span of this element. Have you seen the U8 already? I see nods and a couple of hands. This is the new UTF-8, the string literal, which also came in C# 11, where we can now basically have a string, but represent it not as a byte, as a span of char, but as a span of byte. JSON, for example, is the definition of JSON, is the specification of JSON is in UTF-8, and all the JSON methods that we have with system text JSON, they are UTF-8 based. And now with that, we can actually have very efficient and very nice operability with those types and with JSON per se. Now we also have this in the other direction, so not index of any, but last index of any, which now goes the other way. So we want the last index of any except 0, 2, or 3, which will be this space here. And again, this also exists as a span overload. Yes, memory extensions. There is more memory. Again, coming to the span, I'm talking a lot about span because there is a lot of new methods in .NET 7 coming that are span related, and this will not get less. I think Stefan Po wrote an article about .NET Core 2.1 when span got released. Span, the new mainstay in .NET. So sooner or later, you will get some collision with span, and this is. A lot of APIs will be taking spans. And we can now very nicely create spans if they only have one element in it. So there is now new constructor overloads that take just an element as a reference. Now this is so that we don't occur any copying. And the span actually refers to the reference and the length. This is now the performance optimization that I meant earlier. I'm having here a struct, which is fairly large. It has, I think it's 24 bytes or something. I have a test, yeah, so it's 24 bytes, which means that as a structs are copied by value. So every time we copy the value to a method or to another local variable, we would copy those 24 bytes on the stack. Now, on the machine I'm running on, 64 bits, a reference is 8-bit size. So this is significantly slower. And if I have high-performance scenarios where I want to pass where I want to get a value from this struct, now as a reference, we can save some time and some copying on the stack. So this is now where the new. If we now have a nullable version of this, previously we had the method getValue or default. But now with this fairly large struct, this would copy those 24 bytes on the stack. But we can get a reference on it, so we only get those 8 bytes. And this is where the new method comes in, the getValueRef or default ref. So there is a lot of refs coming on, and the ref is a managed reference. And there is several overloads to that. So we can get a reference out of this default value. And since it's a reference, we can now actually, do I have this example? No, I don't have this example. Never mind. All right, and one more throw helper that we have is on the object is post exception. So we can now just say, I'm having here a disposable that if I dispose it, setting the dispose to true, and if I call this method, previously I had to say if disposed, throw new object disposed exception. And again, this would prohibit inlining in some scenarios, but there is now this nice throw if throw helper where we just pass in the Boolean condition and this instance so that this exception gets thrown nicely. All right, and now let's have a look at two more improvements. I'm looking at what is the most interesting stopwatch. So I'm having a test here where if I want to measure time between two places, previously I had to create a new stopwatch and then get an elapsed on it. But a stopwatch, I think that creating a new type stopwatch is, I think the default overhead of a reference type of a class is 24 bits, and it has a long, so that's then adding up to something like 40 bits. And if I'm in a fast scenario but still want to get timing between 2 points, we could previously get this already, the timestamp. Now we have a new method, the get elapsed time, where we pass in the previous start point and can now nicely get time between those instances rather than using stopwatch new. And this improves performance a little bit. So in the test, I'm now having both versions, stopwatch start new, getting the elapsed, and the new version via get elapsed time from the previous timestamp. And that stopwatch saves us those 40 byte of allocations, and it's also a tiny little bit faster. And let me select one last thing from the list. Time is short. We now also have tar support in .NET. Not showing this example. There is also a new abstraction, the DbDataSource, an ADO.NET abstraction, which creates connection strings for us. And the final feature I want to show is a little bit of I/O. So if I wanted to create a temporary file, previously, what was the method called? I think get temp path. But this would only get the path to this temporary file. I still would need to create it. But in the meantime, somebody else could have created it, so it wasn't 100% safe. Now there is a new method which actually creates a new temporary directory. So in, for example, in Windows, it would be somewhere in user/temp, and create it directly. So I get a reference, I get a hold to this directory, but it's also created already, so I can use it immediately. And we also get Unix file modes. Now, this isn't supported on Windows, this is why I have a gouge here, but on Unix systems, we can now set the Unix file modes, such as user read, user write, and so on. And for the final thing, we now have a new nice helper method. So if we want to get, where is it? There it is. If we want to get the contents of a file as an async enumerable, we can now do this via the read lines async. And now this async enumerable, we could asynchronously enumerate via a wait for each, var line in those lines. And this is another nice accelerator how to access files in .NET. And with that, I want to link to some documentation. So I'm having here some links that talk about all the API changes. There is actually a repository which links all those changes. So we can, for example, have a look at let's have a look at system. And we see all those changes. We see that all these primitive types, the byte now has all the interface, the generic math additions. So there is a lot of changes in .NET. I'm afraid we couldn't get a look at all of them today. There is way too many. I'm also linking some further blog posts. For example, what has improved in performance in .NET 7, and also linking to the API reviews. So they are happening, the API reviews are actually happening twice per week. Not this week because it's also NDC and MS build, but twice per week the .NET team is reviewing those BCLs and streaming this on YouTube, so you can, if you want, join this session and get a look at how the team is actually deciding on designing and implementing new APIs into the .NET BCL. And this is it. This is what's new and improved in the .NET 7 BCL. If you go to all of the code that you saw and more is published on GitHub. You can go to this repository. Or if you go to flashover.net/NDC Oslo 2023 API, you get to the previous slide where also my contacts listed. If you have any questions that I'm afraid I can't answer now because time is running short, maybe one. Is there one question perhaps? I guess it's lunchtime, isn't it? Then, thank you very much.